Welcome to Cosmic Wonders. Today we're embarking on, well, a journey through the grand timeline of the cosmos. We're exploring the major epochs that have shaped the universe as you know it.
It's a truly epic tale, isn't it? Starting from conditions almost unimaginable to us now and leading eventually to this vast and complex universe we observe today. It's quite something.
Okay, let's dive right in, right from the very beginning. Our understanding of the universe's birth and evolution, well, it has come a long way, hasn't it?
Oh, absolutely.
It all seems to start with something called cosmic inflation around, what, 13.8 billion years ago?
That's the number, yeah. And for just a tiny, tiny fraction of a second, the universe expanded incredibly rapidly.
Faster than light, even.
Exactly. Faster than the speed of light. Which sounds impossible, but space itself was expanding.
And what actually kicked that off, do we know?
That's still a huge question, a topic of really intense research. Some theories suggest it might have been sort of an inherent property of space-time itself. We're still digging into that.
Right. And here's where it gets really interesting for you listening. This incredibly brief period, this inflation, it had some pretty significant consequences for the universe we see all around us.
Absolutely. One key thing is the universe's observed flatness on the largest scales.
Flatness. How does that work?
Well, think of it like this. If you take something curved, like a balloon, right?
Yeah.
And you blow it up enormously, really huge,
Okay.
to a tiny ant walking on its surface, it would look basically flat. Inflation stretched the early universe so dramatically that any initial curvature would have just been smoothed right out.
So it's like the universe got ironed out in this blink of an eye. Wild.
Yeah, and it didn't stop there, did it? Inflation also kind of set the stage for everything else forming, like for you and me, eventually.
Exactly. The thinking is that inflation magnified tiny density fluctuations that existed at the quantum level,
Hmm.
the realm of the very, very small. Little wobbles.
Quantum jitters, almost. That's a good way to put it. And these tiny variations in density, they acted like seeds. Through the pull of gravity over vast stretches of time, they eventually grew into the large-scale structures we see today.
Like galaxies and galaxy clusters.
Precisely. So imagine the seeds of these massive things you see in the sky were sown in that initial, minuscule fraction of a second.
It's just mind-bending, thinking that the galaxies you might see tonight trace their origins back to those tiny quantum effects.
Okay, so after this super fast expansion, inflation stopped. What happened then? That brings us to the Big Bang, right?
That's it. When inflation ended, all the energy that had been driving that expansion, it didn't just disappear. It transformed into matter and light.
And that's the Big Bang.
That's what we generally call the Big Bang, yeah.
Yeah.
In the very first second after that, the universe was just this incredibly hot, dense soup of light and fundamental particles.
How hot are we talking?
Almost unimaginably hot, like around 100 nonillion degrees Celsius, something like
Yeah.
that. Wow. Okay. Try wrapping your head around that heat. And in those first few minutes, some really crucial chemistry happened, didn't it? Laying the foundation for the elements we're all made of, that you're made of.
Yes, exactly.
Yeah.
The era of nucleosynthesis, it followed right after. In this period, protons and neutrons were whizzing around, colliding, and these interactions created the very first elements.
Which were?
Primarily hydrogen and helium, loads of it, plus trace amounts of lithium and beryllium.
So the basic building blocks.
The absolute basics, yeah. It's pretty amazing to think that these fundamentals started coming together in those very first moments.
And it's even more mind-blowing that most of the helium you find in the universe today was actually forged in that incredibly brief window, like the first 5 minutes.
It really is. After about 5 minutes, maybe a bit more, the universe had expanded and cooled enough that this early type of element formation, well, it pretty much stopped.
Okay.
But the universe was still far too hot for atomic nuclei to actually capture electrons and form stable neutral atoms.
So what did that mean for how the universe looked? Could you see anything?
Not really. It meant the cosmos was still opaque. Imagine a thick fog. All those free electrons were constantly scattering light, bouncing photons around, so light couldn't travel very far.
Right, a cosmic fog. So the universe was full of light and these new nuclei, but you couldn't see through it. That sounds pretty dramatic. How did we get from that state to the transparent universe you and I see now?
That transition happened during a really pivotal period called recombination. This was about 380,000 years after the Big Bang.
Okay, 380,000 years later, what changed?
The universe had cooled down significantly by then to around 3,000 degrees Celsius. Still hot, but cool enough for atomic nuclei, mostly hydrogen and helium, to finally capture electrons and become neutral atoms.
Ah, so the electrons got bound up. Let's unpack the impact of that for you listening. The universe went from foggy to clear, basically.
Basically, yes. With electrons now bound to atoms, there weren't nearly enough free electrons left to scatter light effectively. So that cosmic fog just lifted, it cleared, making the universe transparent for the very first time.
So light could finally travel freely?
Exactly. Across vast distances. You can think of it like, the fog lifting after a really dense fog, suddenly revealing the landscape.
And this event, recombination, it also gave us something else, didn't it? A kind of snapshot of the early universe that we can still see today.
You got it. The formation of these first neutral atoms, it also released its own light, a burst of photons from that moment. And this light, which has been traveling across the expanding universe for billions and billions of years, well, we can still detect it today.
That's the cosmic microwave background, the CMB.
That's the CMB. It's literally the oldest light we can observe, like a baby picture of the universe.
Wow.
And it's an incredibly valuable source of information about those early times, about what things were like back then.
And you mentioned earlier, within this CMB, there are those tiny temperature fluctuations, the seeds of galaxies. It's all connected.
It all ties together beautifully, yeah. Those tiny hot and cold spots in the CMB map directly onto the density fluctuations that inflate and amplified.
Amazing. But okay, after recombination and the release of the CMB, things didn't immediately light up with stars, did they? There's still a long stretch of darkness, the Dark Ages.
That's correct. Following the emission of the CMB, the universe entered what we call the Dark Ages.
Why dark? I thought it just became transparent.
Well, it was transparent to the CMB photons, the really long wavelength light, but at shorter wavelengths, like visible light, it actually became opaque again for a while.
Oh, right. Why?
Because of all those newly formed neutral hydrogen atoms, they're very good at absorbing certain wavelengths of light. So for roughly the next 200 million years, maybe a bit longer, the cosmos was essentially dark because no stars had formed yet to produce new light.
So picture this for yourself. A vast universe filled mostly with hydrogen and helium gas, transparent to microwaves, but dark in terms of visible light. No stars yet. A truly dark and maybe quiet place.
Pretty much. Just this sea of neutral atoms cooling and swirling under gravity, waiting.
Waiting for what? How do we get out of that darkness and into a universe filled with the starlight you see?
The key, as always in cosmology, it seems, was gravity. The gas in the universe wasn't perfectly uniform. Remember those density fluctuations?
The seeds, yeah.
Right, so there were slightly denser regions, slightly cooler regions. These denser clumps of gas had a stronger gravitational pull. They started attracting more and more matter over time, pulling it in.
Okay, so clumps getting bigger.
Bigger and denser. As these clumps grew, their centers became increasingly hot and pressurized. Eventually, the pressure and temperature right at the core of these collapsing gas clouds became so extreme that nuclear fusion ignited.
And boom, the lights came back on.
Exactly. The first stars were born.
But these weren't like our sun or the stars you see twinkling now, were they? I heard they were different.
Oh, very different. These first stars were absolute behemoths, monsters. We think they were significantly larger and much, much brighter than our sun, maybe 30 to 300 times more massive.
Wow.
And millions of times more luminous, burning incredibly hot and bright, but also living very short lives because they burn through their fuel so fast.
So these giant short-lived stars started popping up. How did that lead to galaxies?
Well, over hundreds of millions of years, these initial stars, massive as they were, began to cluster together, pulled by their mutual gravity. Eventually, these clusters merged and grew, forming the very first sort of proto-galaxies, and then the earliest true galaxies.
So the darkness finally began to give way to these pinpricks of intense light, which then grew into the first galaxies.
That's the picture, yeah. The universe started lighting up again.
So light finally returned. But I remember reading that even with these stars, their light initially had a hard time traveling very far for you to see across the universe.
That's right. Because remember, the space between these first stars and galaxies was still filled with all that neutral hydrogen gas left over from the Dark Ages.
Ah, the absorber.
Exactly. But the intense ultraviolet radiation pouring out from these massive first stars was energetic enough to interact with that hydrogen. It started ionizing the hydrogen atoms, stripping the electrons away from the protons again.
So breaking the atoms apart.
Basically, yes. Turning the neutral gas back into a plasma of electrons and protons. This process is called reionization.
Reionization, okay.
And as this process continued, as more stars formed and pumped out more UV light, that starlight could travel greater and greater distances through the gas.
It was like the stars were carving out bubbles of transparency around themselves.
That's a great analogy. These bubbles of ionized gas grew and merged, allowing light to penetrate further and further, ionizing more and more of the hydrogen gas.
So it was a gradual clearing, driven by the stars themselves, making the universe increasingly transparent for light, like the kind you see.
Precisely. By the time the universe was about, say, 1 billion years old, the vast majority of that intergalactic hydrogen gas had been reionized by the cumulative light from all these early stars and galaxies.
And that made the universe transparent to visible light, pretty much as we observe it today.
Yep, that's the state we're in now, largely. It's a remarkable transition, really, from a dark, neutral, opaque cosmos to the bright, ionized, transparent one you inhabit.
It really is incredible to trace that journey from opaque fog to dark transparency to light-filled transparency. But the story doesn't end there, does it? The
Yeah.
universe is still evolving, and in some pretty surprising ways that affect its long-term fate.
Indeed. For a long time, the sort of standard thinking was that the universe's expansion, the stretching that began with the Big Bang, was gradually slowing down.
Which makes sense, right? Gravity, everything pulling on everything else should act like a brake.
That was the logical assumption. It seemed inevitable that gravity would eventually, slow things down, maybe even reverse it eventually in a big crunch.
Yeah.
So that fell out of favor.
But then came a rather unexpected discovery, wasn't it? In the late 1990s, something involving exploding stars that changed our whole picture of how the universe expands for you.
Yes, a game changer. Astronomers were observing very distant supernovae. These type I as supernovae are great cosmic mile markers because they have a known intrinsic brightness.
Standard candles.
Exactly, standard candles. And they found that these distant supernovae were fainter than expected for their redshift, for how far away they should be based on a slowing expansion.
Fainter means farther away.
Farther away than predicted. The only way that made sense was if they were actually receding from us faster than our models suggested. The expansion hadn't been slowing down as much as we thought. In fact,
It was speeding up.
it was speeding up. The universe wasn't just expanding, its expansion rate was actually accelerating.
Mind blown again. So the universe isn't slowing down, it's hitting the gas. What on earth is causing that? What's the driving force behind this acceleration that's shaping the cosmos for you in the future?
Well, that is the big question in cosmology right now, perhaps. Scientists hypothesize the existence of a mysterious substance, or maybe energy, called dark energy.
Dark energy. Okay. What is it?
We don't really know what it is, fundamentally. That's the honest answer. But it appears to be some kind of intrinsic energy of space itself, exerting a sort of repulsive force, like anti-gravity on the largest scales,
Pushing things apart.
pushing everything apart and counteracting even overwhelming gravity over cosmic distances. It makes up, we think, almost 70% of the total energy density of the universe.
Wow, most of the universe is the stuff we don't understand.
Pretty much is one of the biggest mysteries out there.
And looking ahead then, based on this dark energy idea and our current understanding, what does the future hold for the universe's expansion? What might you find fascinating about where it's all heading?
Well, the current cosmological models, based on all the evidence, including the CMB and those supernovae, strongly suggest that the universe will continue to expand. And not only expand, but expand faster and faster, driven by this dominant dark energy. So likely heading towards an indefinite expansion.
Wow. Not a big crunch, but maybe a big rip or just endless expansion.
The details are debated, but yeah, continued acceleration seems to be the leading prediction right now. It's a truly mind-boggling journey we've traced, hasn't it? From that incredibly hot, dense state just after inflation through nucleosynthesis, recombination, the dark ages, the first stars, reionization.
All leading to this vast, expanding, and accelerating universe we see today. So many incredible epochs, each playing such a crucial role in shaping the cosmos you inhabit.
It really is.
And it's just a testament to human curiosity, isn't it? And scientific investigation that we can piece together this grand narrative, this amazing history of everything.
Couldn't agree more. And there are still so many questions left to answer.
Yeah, absolutely. Well, that's all the time we have for this particular deep dive. Thank you for listening to this Cosmic Wonders.